2.3 is on linear equations or linear first order differential equations. So we've already seen the basic format of a linear equation for differential equations. So this is the basic form for first order linear would be a1x dy dx plus a naught x y equal to b of x. Where, and this is important, critically important to be linear, where a naught, I'll just put a naught. So a naught and their functions, right? A1 and b only depend on x. So, and not y, right? So a naught of x, a of x, and b of x only depend on x and not y. So you can't have another y in there. Also note, and this gets a little later into our book, but I thought I'd make a note here. Note if b of x equals 0 in the equation above, then, actually I wrote that wrong. So if b of x equals 0, then that first order linear equation is said to be homogeneous, and 1 is homogeneous. And for those who've had linear homogeneous systems, right, it's always said equal to 0 is the concept. So the standard form is what you're going to be writing in. So standard form is kind of where you begin, looks like this. It's dy dx plus capital P of x, y equal to q of x. So to get that, basically you divide both sides by a1 of x. All right, so where P of x then would be a naught of x over a1 of x. So 1 there. And b of x would be, or I'm sorry, q of x would be b of x over a of x. So, and q of x then, of course, would just be b of x over a1 of x. So you're just dividing out, of course, by this term. So if you have a factor there, then you just divide out by it, and you get this standard form. So this is what we're going to be working with. Okay. So what we do next is basically build the form we want. So I'm going to bear with me for a second. So now find mu of x so that the left-hand side of looks like this. Let's say left-hand side has this form. So you end up with mu of x dy dx plus mu of x p of x y is equal to mu of x q of x. So what we are looking at is really this, And if you consider mu of x, y, the derivative is that form. So if you take the derivative of mu of x, y, you get the derivative is mu of x, y prime. So the first times the derivative of the second plus the derivative of the second times the first. So it's that form. So then, if you have that, this requires, so basically what we get then is this. So this requires mu satisfy mu prime equal to mu times p. It's like mu times a constant. So think. So when you have like the derivative of something is itself, what is that? And then it could be times a constant. So you want to think e to the kt. So its derivative is itself. Now you might get an extra factor in there of the k, but its derivative is itself. So think that. So what you do is you write d mu dx is mu p of x. And that is a separable equation. So you can rewrite that as 1 over mu d mu equal to p of x dx. And then if you integrate both sides, so integrate on both sides, what you have then is 1 over mu d mu equal to the integral of p of x dx. So when you get that, you get natural log absolute value of mu equal to the integral of p of x dx. And then if you solve that for mu, and then you'll be able to drop the absolute values because it's positive and stuff. Oops, let's try to fix that. Okay, so eventually you'll be able to drop those. So what you get then is that is equivalent to, when you solve, mu of x equal to e raised to the integral of p of x dx. So because this is always positive, you can drop those absolute values. I don't think they go over that so much in the book when I read through it, but that's what they're saying. So what you have then is your mu of x is equal to e to the integral of p of x dx, and then you substitute in, and I called, where did I go back up here? We're going to call this equation 5 back here. So you substitute into 5, equation 5 above, and I'm following the book format as well. Then you get d dx of mu of x y equal to mu of x q of x. Now if you integrate, you get the integral of d dx. So integrate on both sides. So the left-hand side is just fundamental theorem of calculus. So it's just mu of x y. So you get mu of x y dx equal to the integral of mu of x q of x. dx. And so the left-hand side just becomes mu of xy equal to whatever that integral is, mu of x q of x dx. And then if you solve for y, you get the actual equation. You get y. So this is the general form. Let's do it like that, I guess. Y is 1 over mu of x times the integral everything above. So it's mu of x q of x dx plus c. Like that. Okay, and that's the general solution. So and is the general solution. So one of the things we need to realize is back here. Let's see if I could find it. So back here, when you have the dx of mu of x y, that's this whole thing here. So this here is this. When you calculate that out, now you have an extra factor possibly, but that's the form you have when you do that calculation. So so then let's look at the method. So that's the derivation basically, and putting this a little more concisely in the method to solve. Let's do that next. So this is I'm just highlighting what's already in the book and hopefully describing it. So this is method for solving linear equations, specifically first order differential equations. So A, standard form. So you write everything in standard form. So it'll be the dy dx plus p of xy equal to q of x. So it may be in that form, probably not, but so you get it in that form first. Then B, so the mu of x is called an integrating factor. So you calculate the integrating factor, mu of x. So, and we calculated that formula already. So that derivation I just showed you is where you get that integral. So mu of x is e raised to the integral of p of x dx. Okay, so that's called an integrating factor. That's really the key to it. What's this derivation up here shows you why you need to get this integrating factor. Okay, so it's from solving this, right? That's what you end up having to substitute in to make this work. It takes a little time to kind of see it, but spend a little time on that to see how that works. Okay, but I suggest we'll do a few examples first, and it starts to click a little better. Okay, so then you multiply, so C, so you calculate the integrating factor. Then you multiply on both sides by mu of x, whatever you end up finding. So you end up getting, and I'll rewrite it, you end up getting mu of x dy dx plus p of x mu of xy, it doesn't matter that order, equal to mu of x q of x. But this left-hand side is just, so this is part you need to remember. You multiplied by that so that d mu of y is above. So that's what that's your intent. So it's really, you're just integrating the right-hand side, which is the mu of x, q of x. Okay, then you solve and you end up getting the equation above. So once you have this form, it's this, and then you solve and get y. So once you solve and get y, that's your general form. Okay, so then from here, like I just said, right here, you integrate on both sides. So there's really two major, well, more than that. Basically, standard form, so you figure out what your p of x and q of x are. Then you have to calculate your mu of x, whatever that ends up being. Once you do that, you just place it here and here, and then it's really about integrating this right-hand side, because this is already done. It's already, you just put it in that form. Okay, so that's the technique. We'll run through the next video a number of examples, or a couple, and then if we need more examples, we'll do them in our problem sessions.